Hello, this is Ahmad Mirabi. In this video, I want to teach a bit of physics. Let's start. So, let's talk about poles of a magnet. The end of a magnet are where the magnetic field is the strongest. So here, the lines are more dense, so we can say the magnetic field is stronger here. And if there is a force of repulsion or attraction, it will be greater near the ends compared to the middle. So these are called poles. The end of a magnet are called poles. Each magnet has two poles, one north pole and one south pole. Okay, like poles repel each other. Unlike poles attract each other. Just like electricity. For example, we have a bar magnet here fixed. If you suspend another bar magnet and you leave it, or you bring it close to this fixed bar magnet, because S and S repel each other, it will rotate like this so that S will be far from S and N will get closer to it. In another case, for example, if this is the case, the suspended bar magnet will rotate such that N will get close to S so that there will be a attraction here. If they're close enough, they will attach to each other. Poles of a magnet always come in pairs. We have no monopole in magnetism. So it's not like electricity. In electricity, we had positive and negative charges in every material. We could separate the positive charge and negative charge. So we have some objects with total positive charge or with total negative charge. But it is not the case in magnets. For example, if you break a magnet into two parts, every part will be a SN magnet. So every part will have a south pole and north pole. If you cut a magnet in half, you get two magnets. So we cannot have monopole in magnetism. Finding geographical pole of the Earth with an experiment. Suspended bar magnet will rotate so that N pole will direct almost toward the north pole of the Earth. So we have a bar magnet here. We suspend it from an aluminium or other material other than iron, nickel, or magnetic material. I think they were iron, nickel, or cadmium, something like this. There are some metals which have magnetic property. For example, aluminium doesn't have magnetic property. So consider this holder is made from aluminium. We need to make sure that there are no other magnets or iron objects near the magnets we are experiencing with. So if a bar magnet is suspended from an aluminium holder, we leave it, it will rotate such that the N pole or north pole of the magnet will show the north pole or the geographical north direction. It is just like a compass. Okay, we'll talk about the compass later. Magnetic induction. If we place a small nail or needle near the end of a magnet, it sticks to the magnet. So here we have a bar magnet. We have some nails here. We have some steel paper clips. If you bring the first paper clip close to this bar magnet, it will attach to it. And then if you bring the second one, it will attach to this one, and then the third one and the fourth one, and it will make a chain of paper clips like this. It will make a chain of nails like this. The fact is, when you bring in the paperclip, first the paperclip will be a magnet itself by magnetic induction. So first, when it is close enough, it will be SN magnet, and then N absorbs N, so it sticks to it. And then another paperclips is the same story. When it is close enough, by magnetic induction, the second paperclips will be a magnet. So S and N, and therefore S sticks to N. This is the way. This is how they attach to the poles of a magnet. So place the next nail near the tip. So the first nail sticks to the bar magnets. Place the next nail near the tip of the first nail. Again, sticks. Repeat this for other nails. We can see that many nails attached to each pole. If we put a cardboard or glass between the magnet and the first nail, so if we put a cardboard or glass here, again this applies, and this phenomenon again repeats. We can do it again as before. We see the magnetic property of a magnet affect without contact with the nails. This phenomenon, that means creation of a magnetic property in a piece of iron without touching, is called magnetic induction. So magnetic induction is when a magnet makes another magnet or another iron like a magnet without touching. Without touching, without contact, it induces magnetic property in a piece of iron. Okay. What is electromagnet? Electromagnet is when, for example, we have a battery here, we have a wire connected to the positive and negative pole, and we have wrapped it around the iron nail. So we need a battery, or we have electric circuit, wire, of course, and iron core. We need iron core or iron piece of iron. So we know from the previous session that current is like this. Current is conventional direction of current is from positive, is the movement of positive charges. So it comes here. So the current in the coil will be like this. And when it is on, which means the circuit is closed, there is a current in this coiled wire. So there will be a magnetic property in this nail. Here it will be S, here it will be N. So this nail will act like a magnet while this current is on. When you turn off this current or you disconnect the wire, the magnetic property will go out, or the magnetic property disappears. So this is good, because when we want the magnetic property we can make it, and when we don't want the magnetic property, simply we can use a switch here and turn off this electric current, and then magnetic property disappears. So electromagnets are widely used in everyday life: house doors, magnetic cranes, electric clocks. These are examples and applications of electromagnets. What factors affect the magnetic strength? Pole N and S of an electromagnet depend on the direction of the electric current. So I'll talk about how I found the S and N poles like this in the upcoming sessions. So when the direction of current changes, for example, if the direction of current is like this, the S and N switch. So depend on the direction of the, so S and N in the electromagnet depend on the direction of the electric current. Number 2, the greater the current passing through the coil, the greater the magnetic property of the electromagnet. So the greater the current, the greater the magnetic property, the greater the magnetic field. Number 3, the greater the number of turns in the coil. How many turns we have here? 1, 2, 3, 4, 5, 6, 7, 8. The greater the number of turns in the coil, the greater the magnetic property of the electromagnet. So this magnet will be stronger, or magnetic fields around this magnet will be stronger and more effective.